We just saw on the robot why we need rotation matrices and homogeneous transformations. Now let's get to the theory. What is a rotation matrix? It's nothing but a mathematical relationship in matrix form, obviously, of the relationship between two coordinate frames with different orientations. So here I've shown one coordinate frame, which is the blue frame. Let's call it the 0 frame, x0, y0, z0, and another coordinate frame, the 1 frame, which is x1, y1, and z1. And for the moment, we are not worried about the origins being different. We are just worried about the orientations. So we will assume both of them have the same origin. So what we are trying to figure out here is, supposing there is a point here in 3D space, let's call it P, and there is this vector P. Now this vector P can be expressed in terms of the components along x0, y0, and z0, and it can also be expressed in terms of components along x1, y1, and z1. What would that relationship be? The components along one of the coordinate frames versus components along the other coordinate frame. That is what we are really trying to establish here. Okay, so let's consider vector P, and let's say P0 is nothing but vector P expressed in terms of components along x0, y0, z0, and similarly P1 is the same vector but with components expressed along the other coordinate frame. So vector P expressed in terms of components along x1, y1, z1. So we can now go ahead and write P0 as P0x along I0 hat or I0 hat, P0y along J0 hat, and P0z along K0 hat, and P1 as P1x I1 hat plus P1y J1 hat plus P1z K1 hat. And we are trying to figure out a relationship between the components over here and the components over here. So we start with taking advantage of the fact that these, so P, P0, P1 are all the same vector essentially, they are all equal. And if I were to write an expression for P0x, can you figure out what that expression would be? It is simply P0 dot with I0 hat. This is obvious, but it's also a little weird because to find P0x along I0 hat, you have to take P0 and dot it with I0, and it works out if you see it. So now, taking advantage of the fact that P1 and P0 are the same, I can also write this as P1 dot with I0 hat, and now I can plug in P1, the expression for P1 over here, and I would get P1x I1 hat dot with I0 hat plus P1y J1 dot with I0 hat plus P1z K1 hat dot with I0 hat. It is starting to look a little bit complicated, but it is really not. All we did was express the first component of P along the x0, y0, z0 frame in terms of a dot product and simply plugged in expression for P1 over here. Now I can go ahead and do the same thing for P0y, and I would get P1x I1 but now dot with J0 hat, and P1y J1 dot with J0 hat, and P1z K1 dot with J0 hat. And similarly, I can do the same thing for the third component P0z, and just to reiterate, P0z is nothing but P0 dot with K0, and P0 is the same as P1, so I can write it as P1 dot with K0, and for P1 I can substitute this entire expression, and again I get this P1x I1 dot with K0 plus P1y J1 dot with K0 or K0 hat, and P1z K1 hat dot with K0 hat. Okay, so now that we have these three equations, we can write them in more compact form, and they would become P0x, P0y, P0z is equal to a matrix multiplied by P1x, P1y, P1z. And looking at this pattern here, I would simply get a bunch of these dot products here in the matrix. So I would get an I1 dot with I0 hat here, I would get a J1 dot with I0 hat, and I would get a K1 dot with I0 hat. And in the second row, I would get I1 dot with J0 hat, J1 dot with J0 hat, and K1 dot with J0 hat. And finally, in the third row, I would get again I1 dot with K0 hat now, J1 dot with K0 hat, and K1 dot with K0 hat. Okay, now that we have done the hard work, this is the most complicated part of writing these matrix relationships. From this point on, it only gets easier. But now that we've done the hard work, now let's look at this matrix and see what this is really doing. This matrix relating components of vector P along x1, y1, z1 to components of the same vector along x0, y0 and z0. So this matrix is called a rotation matrix going from frame 0 to frame 1. So I'm calling it R, standing for rotation matrix going from frame 0 to frame 1. And if I take the components of P in the one frame and then pre-multiply it with this matrix, I will get the components, sorry I missed it, components of P in the 0 frame. Okay. Now this is an interesting matrix and has a bunch of interesting properties. One, these are both always the same vectors, right? Physically it's the same vector, it has the same magnitude and same direction, which means no matter how much the rotation is between these two frames, the magnitude of this vector, the P1 vector and P0 vector would have to be exactly the same. That would automatically mean that our matrix cannot scale up a vector or scale down a vector. Do you know what that translates to in terms of mathematical properties? It means that R would have to have determinant 1. Do you agree? Do you think that's what it is? Okay, go back and look at determinants and see if that gives you that property. If R always has determinant 1, would that mean that there is no scaling between these two vectors? Okay, so that's one. Second, obviously all of these entries are now dot products between unit vectors only. So a dot product between two unit vectors can never be more than 1, right? So all of these entries would be entries less than 1, right? Or rather between +1 and -1. These are also probably something very familiar to you. You might have seen in mathematics in, maybe some of your earlier courses. These are nothing but direction cosines, right? It's just an arrangement of direction cosines. Now this also has an interesting name. So this R is said to be a vector in SO3. SO3 standing for special orthogonal group of order 3. Now what is this thing about orthogonal group? So we'll come to that in a second. So let's save this. This another interesting aspect here which makes this an orthogonal matrix. Okay. Now if instead of first writing components of P along the 0 frame, if I had done the reverse, right? So if we do the reverse, meaning what? If I had written P1x, P1y, P1z, and if I had gone through exactly the same set of steps, so P1x means P1 dot with I1, and since P1 and P0 are the same, I would then write that as P0 dot with I1, and for P0 I would have plugged in this whole expression, and if I go through that and do the same thing for all three and then write it in matrix form, and you can do that, it's relatively straightforward, then can any of you figure out without going through the entire math how different would that matrix be as compared to this matrix? And of course this would have a different name because this is now P1 on the left hand side. So this would still be a rotation matrix, but this would be a rotation matrix that is going from frame 1 to frame 0. Now the question is, how different would R1 to 0 be from R0 to 1? Have you figured it out? It turns out you will have all these same dot products but arranged in a different way, right? So this would be nothing but simply the transpose of this matrix, right? So once you work it out, you will see R1 to 0 is R0 to 1 transpose. But you guys know how to work with matrices. When you have a vector is equal to a matrix times another vector, if you wanted the reverse relationship, you could take the inverse of this matrix and pre-multiply on both sides. So then you would get an expression similar to this. So it turns out this is also the same as R0 to 1 inverse. So this is an interesting property of these matrices. The inverse of a rotation matrix is nothing but the transpose of the matrix. This makes life a lot easier. You know, computing inverses are hard, but computing transposes are easy. I would always, I would any day take this situation where if to compute an inverse, I just have to compute a transpose. So that's why these are called orthogonal matrices, because the inverse of the matrix is the transpose, and this is true for all rotation matrices. This is just an example that we did, but this is a general enough derivation that this is applicable to all rotation matrices. They always have determinant 1, they are always orthogonal, and they are said to be in SO3. They never change the magnitude of the vector. And it's just a matrix multiplication to transform from coordinates in one frame to the other frame. Now we can use this a little bit in more complex situations where we are not just talking about 2 frames, but we are talking about a sequence of rotations. And as we saw in the robot, there are a number of joints, each one could be rotating a different amount, and you want to be able to do these calculations repeatedly over and over again. So now let's look at a different situation where you still have this, but you have another rotation sequentially after this.